first.
Pause. What you see behind me was one of the most powerful moments in the history of science. You may recognize J. Robert Oppenheimer by the movie directed by Christopher Nolan. As a physicist and leader of the Manhattan Project, he helped create something that haunted him for the rest of his life. But here's the thing. The physics behind that bomb wasn't just destruction. It's the very same force that makes life on Earth possible. Okay, resume.
In a test in the United States New Mexico desert, then 5,000 miles away at Hiroshima, and then again at
I think we should go back to the very beginning, how all of this began.
The late 19th century marked a turning point in science. For centuries, atoms were believed to be solid, stable, and indivisible. However, a series of unexpected discoveries would begin to change everything. In 1895, Wilhelm Röntgen was experimenting with cathode ray tubes when he noticed a strange glow coming from a nearby screen. He discovered X-rays, an invisible form of radiation capable of passing through solid objects. Dense materials like bone absorb more of these rays, which created shadow-like images. This breakthrough transformed medicine, allowing doctors to see inside the human body without surgery for the first time. Just 1 year later, in 1896, Henry Becquerel made another groundbreaking discovery while studying radium salts. He found that they emit visible rays on their own, even on exposure to sunlight. This phenomenon, later known as radioactivity, revealed that atoms were not stable after all, but instead they could release energy from within. Building on this work, Marie Curie and Pierre Curie conducted further research into radioactive materials. In 1898, they discovered two new elements, polonium and radium. Their work proved that radioactivity was a property of certain elements and introduced the concept of nuclear decay. They also gave this powerful phenomenon its name, which is radioactivity. At the start of the 20th century, the atom was thought to follow the plum pudding model, where electrons were embedded in the positively charged sphere. In 1909, Ernest Rutherford, along with Hans Geiger and Ernst Marsden, tested this idea by firing alpha particles at a thin sheet of gold foil. Most particles actually passed straight through. However, some were deflected at large angles, and a few even bounced back. These unexpected results reveal that atoms were mostly an empty space with a tiny, dense, positively charged nucleus at the center. And following in 1911, Rutherford introduced a nuclear model of the atom, which completely transformed atomic theory. In 1913, building on their idea, Niels Bohr proposed that electrons orbit the nucleus in fixed energy levels. This idea introduced early concepts of quantum mechanics and helped explain atomic stability. Despite these advances, one piece of the atom was still missing. In 1932, James Chadwick discovered the neutron, the neutral particle within the nucleus. By bombarding the beryllium with alpha particles, he detected radiation that carried no charge but had mass similar to protons. This discovery explained why atomic mass is greater than the number of protons and revealed the existence of isotopes. Now that scientists have figured out what's inside the atom, new questions came up. Where does all that energy come from? The answer lies in the relationship between mass and energy, which is where Albert Einstein comes in. Let's see what he's discovered.
Well, we have assumed that mass is always conserved in physics. However, if we look deeper at a subatomic level, the measured mass of a nucleus is always less than the sum of the masses of the individual protons and neutrons. The difference in mass is called the mass defect, and we measure the masses of the nuclei and nucleons in unified atomic mass units U. 1 U is 1/12 of the carbon-12 atom, 1.66 times 10 to the power of -27 kilograms. The missing mass isn't actually gone, but it has been converted into energy. When nucleons come together to form a nucleus, a massive amount of energy is released. Okay, so we've got the missing mass, but where does it actually go? Well, in 1905, I introduced an idea that completely changed how we understand energy. I proposed that mass and energy aren't separate, but are actually interchangeable. In other words, mass can turn into energy. I described this relationship with my famous equation E equals mc squared, where E represents energy, M is mass, and C is the speed of light, which is 3 times 10 to the power of 8 meters per second. Because of this, even a tiny amount of mass can produce an enormous amount of energy. To put it into perspective, just 1 kilogram of matter could release about 9 times 10 to the power of 16 joules of energy. In nuclear physics, though, joules are often too large to work with. Instead, we use a smaller unit called the mega electron volt, or MeV. 1 MeV is equal to 1.6 times 10 to the power of negative 16 joules, and when working with atomic mass units, 1 unit of mass is roughly equal to 934 MeV of energy. So now we may know where the missing mass goes. But what is energy actually doing inside the nucleus? I'll leave the rest to Paige because I am getting quite tired.
Thanks, Mr. Albert. That energy is known as nuclear binding energy, which is the energy that holds the nucleus together and keeps it stable. Think of it like the energy needed to destroy a building into pieces. The stronger the building, the more energy it takes to destroy. So the higher the binding energy, the more stable the nucleus. And this is where it gets really interesting. Binding energy is equal to the mass defect, that missing mass we calculated. That is exactly how much energy was released when the nucleus formed in the first place. Same thing, different form, where mass went in and energy came out. To understand what really happens inside the nucleus, scientists use something called nuclear equations. These equations track particles during a reaction using nuclide notation, and for any reaction to work, 3 rules must always be followed. 1. The number of protons must stay the same. 2. The total number of nucleons, protons, and neutrons must stay the same. And 3. The overall mass energy must be conserved. Let's look at an example wherein a helium nucleus collides with a nitrogen-14 nucleus. It can transform into oxygen-17 and a hydrogen nucleus. At first glance, everything seems balanced, but here's where it gets interesting. When scientists calculate the total mass before and after the reaction, they find something unexpected. The products actually have a slightly more mass than the reactants. That difference might seem tiny to us, which is just about 1.277 times 10 to the power of negative 3 atomic mass units. But in nuclear physics, it is a huge deal. Using Albert Einstein's idea that mass can turn into energy, this mass difference is equivalent to about 1.2 MeV. But since the products are heavier, this energy needs to be supplied. That means this reaction won't just happen on its own. The helium nucleus has to come in with enough kinetic energy, which is at least 1.2 MeV, to make the reaction possible. This brings us to an important idea in nuclear physics, the stability of nuclei.
Inside every atomic nucleus, there are nucleons, which are positively charged protons, and neutral neutrons. Now, based on basic physics, all these protons should be pushing each other apart because of electrostatic repulsion. So, why doesn't the nucleus just fall apart? The answer is the powerful force, which is called the strong nuclear force. It acts at very short distances and is strong enough to overcome the repulsion between the protons, holding the nucleus together. The stability of the nucleus depends on the balance between these two forces, which are the attractive strong nuclear forces and the repulsive electric force. Scientists measure the stability using something called binding energy per nucleon. The higher the value, the more stable it is. If we look at a graph of binding energy per nucleon right here, we can divide it into 3 regions. In region A, we have light nuclei with low binding energy, meaning they are less stable. These nuclei combine through nuclear fusion to form larger, more stable nuclei. In region B, we will reach the peak, which is around 8.8 MeV per nucleon. This is where nuclei are the most stable. A well-known example is iron-56. Then, in region C, we see very heavy nuclei. As nuclei get larger, stability decreases. The strong nuclear force only works over short distances, but the repulsive force keeps increasing as more protons are added. To stay stable, these nuclei need more neutrons, but even then, they can become unstable and split apart. This is where nuclear fission happens. Both fusion and fission move nuclei towards a more stable state with higher binding energy per nucleon, and when it happens, energy is released. So, if lighter nuclei are more stable, how do they become more stable? Well, it uses a process called nuclear fusion, which is when two light nuclei come together to form a larger nucleus. When they do, energy is released because the new nucleus is more stable and has a higher binding energy per nucleon. But fusion isn't easy. Since nuclei are positively charged, they naturally repel each other. So before they can fuse, they have to overcome this strong electrostatic repulsion. At the same time, there's the strong nuclear force, an attractive force that can bind them together. However, it only works at extremely short distances. So, the nuclei have to get really close before fusion can happen. That is why fusion requires extreme conditions. The first one is very high temperatures, which give the nuclei enough kinetic energy to move fast and overcome repulsion. Second is very high pressure, which increases the chances of collision, making fusion more likely. Once the nuclei are close enough, the strong nuclear force takes over and the energy used to push them together is released, often in even greater amount. A perfect example of fusion is the Sun. Inside its core, hydrogen nuclei fuse through a series of reactions to eventually form helium. This process continuously releases energy, which is what powers the Sun and provides energy to Earth. As fusion continues, elements can be built step by step, from hydrogen to helium, then to heavier elements like carbon and oxygen. Each step releases energy because the products are more stable, but this only works up to a point. At elements like iron, the nucleus reaches peak stability. Beyond that, fusion no longer releases energy but actually requires it. Instead of joining nuclei together, what happens if we split them apart? Nuclear fission is the opposite of fusion. It involves splitting a large unstable nucleus into two smaller ones. And just like fusion, this process releases energy. That's because the smaller nuclei formed are more stable with a higher binding energy per nucleon. Fission usually starts when a neutron is absorbed by a heavy nucleus. This makes the nucleus unstable, causing it to split into two smaller daughter nuclei. A classic example is uranium-235. When it absorbs a neutron, it can split into krypton-92 and barium-141, releasing more neutrons and a large amount of energy. Those extra neutrons are important because they can trigger more fission reaction. This creates a chain reaction where one split leads to many more. Heavy nuclei are more likely to undergo fission because they are far less stable. As nuclei get larger, the strong nuclear force, which only works in short distances, cannot fully hold everything together, while the repulsive force between the protons keeps increasing.
However, not all nuclei stay stable forever. Some are unstable, and when they are, they naturally try to become more stable. Radioactive decay is when an unstable nucleus releases particles or energy to reach a more stable state. Radioactive decay has two key features. It is random and spontaneous. Random means we can't predict exactly which nucleus will decay next. Even in a stable sample, the number of decays we measure can fluctuate unpredictably over time. At the same time, radioactive decay is spontaneous. It doesn't depend on temperature, pressure, or the environment. Whether an atom is deep inside a reactor or sitting in a lab, it has the same chance of decaying. This process is called radioactive decay. To better understand how radioactive decay works, let's imagine something simple, like rolling a dice. If you roll a few dice, you might expect that some of them will land on 6. But if you roll more dice, you'll probably get more 6s. But here's the thing. You can predict how many 6s you'll likely get, but you can't predict which specific dice will land on 6. That's exactly how radioactive decay works. It's random. Now imagine starting with thousands of dice. Every time a die lands on 6, you remove it, just like a nucleus that has decayed. After each round, fewer dice remain. And interestingly, the number of dice doesn't decrease in a straight line, but rather it follows a pattern. After a certain number of rounds, about half of the dice are gone. Then after the same number of rounds again, half of the remaining dice disappear. This pattern is called exponential decay. In nuclear physics, we describe this using something called half-life, which is the time it takes for half of a radioactive sample to decay. For example, if a substance has a half-life of 3 minutes, then after 3 minutes, only half of it remains. Then another 3 minutes, only a quarter remains. So while we can't predict exactly when a single atom will decay, we can accurately predict how a large group will behave over time. So now you may wonder, if radioactive decay is random, how do scientists actually measure how fast it happens? Well, this is where the concept of half-life comes in. Half-life is the time it takes for half of the radioactive nuclei in a sample to decay. Different isotopes have very different half-lives. For example, uranium-238 has a half-life of about 4.5 billion years, while radon-222 only lasts about 3.8 days. Some isotopes decay even faster, like astatine-217, which has a half-life of just a fraction of a second. What makes half-life so useful is that it's constant. Half-life doesn't depend on how much of the substance you have or how long it has already been around. After one half-life, half of the nuclei remain. After 2 half-lives, only a quarter remain. And this pattern continues on and on. So even though individual decay is unpredictable, half-life helps us give a reliable way to understand how radioactive materials change over time. Unfortunately, when scientists measure radiation, things aren't always as straightforward as they seem. Even without a radioactive source, a detector still records counts. This is due to background radiation, which is the ionizing radiation that's naturally present all over us. Background radiation comes from many sources. Some are natural, like cosmic rays from space, or radioactive materials in rocks, buildings, and even the food we eat. Others are artificial, such as remnants from nuclear testing or emissions from power plants. Because of this, scientists have to actually be careful. To find the actual activity of a radioactive source, they first measure the background count rate on its own. Then, they subtract it from the total count rate measured from the source present. This gives the corrected count rate, which represents only the radiation coming from the source itself. It's also important to remember that detectors don't capture everything. They only record particles that happen to travel towards them, but radiation is emitted in all directions.
Now, how do we see it mathematically? To do that, scientists use 2 important quantities, the decay constant and activity. The decay constant, represented by lambda, tells us the probability that the nucleus will decay in a given amount of time. In other words, it describes how likely decay is to happen. Now, if you look at a sample with a large number of nuclei, the rate at which they decay depends on how many are still left. The more nuclei you have, the more decay you'll get. As the number decreases, the rate of decay also slows down. This relationship is written by the equation dn over dt equals to negative lambda n, where the negative sign simply shows that the number of undecayed nuclei is decreasing over time. From this, we define the activity, which is the rate of decay of the sample. Activity is given by A equals to lambda n. This tells us how many decays are happening every second, and it's measured in becquerels, where 1 becquerel means 1 decay per second. This is useful because while we can't count every single nucleus in a sample, we can measure its activity, and from that, we can work backwards to understand what's happening inside. Now that we've defined activity and decay constant, we can describe radioactive decay over time. The number of undecayed nuclei both decreases randomly and follows a very clear pattern called exponential decay. This is written in the formula n equals to NO e to the power of negative lambda t. Here, NO is the original number of nuclei, and N is how many remain after time t. What this means is that the number of nuclei decreases by the same fraction over equal time intervals, which is why half-life stays constant. Since activity depends on the number of nuclei, it all follows the same pattern with the formula. So A equals to AOE to the power of negative lambda T. In fact, this relationship applies to anything we measure in radioactive decay, whether it is activity, number of nuclei, or even the count rate detected. So we can generalize this as X equals to XOE to the power of negative lambda T. Even if we can't directly measure the number of nuclei, we can measure count rate and still determine important values like the decay constant and half-life, which is incredibly useful in experiments. Now, using the exponential decay equation, we can actually connect the decay constant lambda with half-life. Remember that after one half-life, only half of the original nuclei remain. So, at times t equals to t half, the number of nuclei becomes half of NO. Then we can rewrite this equation as half NO equals to NOE negative lambda T. Simplifying this equation, we got half equals to E negative lambda T. Now taking the logarithm of both sides, we get T half as equals to ln2 over lambda. Now we can simplify this again, equals to T half equals to 0.693 over lambda. This relationship is incredibly useful as it links something we can measure easily, such as half-life, to something more fundamental, like the decay constant that controls how fast a substance decays.
So now that we understand how nuclear decay works mathematically, how is this actually used in the real world? One of the most important real-world applications of nuclear physics is the generation of electricity through nuclear power plants. These plants work using nuclear fission, where heavy nuclei like uranium-235 or plutonium-239 are split when struck by neutrons. This process releases a huge amount of energy as heat, along with more neutrons that keep the reaction going in a chain. The heat is then used to produce steam, which spins turbines connected to generators and produces electricity. One major advantage of nuclear power is efficiency. A small amount of fuel can generate a massive amount of energy, and unlike fossil fuels, nuclear power plants do not release carbon dioxide during operation, making them important in reducing greenhouse gas emissions. They also provide a steady and reliable energy supply since they don't depend on weather conditions like solar or wind power. However, nuclear power also comes with challenges. Radioactive waste can remain dangerous for thousands of years, making safe storage a long-term issue. There have also been major nuclear accidents, such as the Chernobyl disaster and the Fukushima Daiichi nuclear disaster, which raised concerns about safety and environmental impact. Because of this, modern nuclear power plants are designed with advanced safety systems to reduce risk as much as possible.
Another thing is that nuclear physics can also be used in transportation. In particular, nuclear energy powers large marine vessels like submarines and aircraft carriers. These vessels use nuclear reactors as their main energy source, allowing them to operate for long periods without refueling. Just like in power plants, the reactor also produces heat through nuclear fission. This heat is used to generate steam, which drives turbines and powers the ship's movement. One of the biggest advantages of nuclear-powered vessels is their endurance. Submarines can stay underwater for months, and aircraft carriers don't rely on constant fuel supply. This makes them especially useful for long-term military operations. There was even an idea to apply nuclear power to aircraft. During the mid-20th century, scientists explored the possibility of nuclear-powered airplanes that could stay in the air for extremely long periods. However, this idea faced major challenges, especially when protecting the crew from radiation and ensuring safety in case of accidents. Because of these risks, nuclear-powered aircraft were never fully developed.
Another is Roentgen's discovery, which is X-rays. X-rays are a type of high-energy electromagnetic radiation with much shorter wavelengths than visible light. They are produced when high-speed electrons suddenly slow down or when electrons shift between inner energy levels in atoms. Because of their high energy, X-rays can pass through soft tissue while being absorbed by denser materials like bone. This is what makes them so useful in medical imaging. In diagnostic radiography, X-rays pass through the body and create contrast images which allows doctors to detect fractures, tumors, or infections without surgery. More advanced techniques like CT scans take this further, producing detailed 3D images of the body by combining multiple X-ray images. X-rays can also be used for treatment. In radiation therapy, high-energy X-rays are directed at cancer cells, damaging their DNA and stopping them from growing. Modern techniques allow doctors to target tumors precisely while minimizing damage to healthy tissue. Beyond medicine, X-rays are also widely used in industry and security. They help detect cracks in metal structures, inspect materials without damaging them, and even scan luggage at airports. Real-time imaging methods like fluoroscopy are also used to guide procedures inside the body, such as in heart treatments. However, X-rays do come with risks. Because they are ionizing radiation, high exposure can damage healthy cells and increase the risk of cancer over time. That's why strict safety measures are always followed to keep exposure as low as possible.
Nuclear physics also plays a role in our everyday life, which is through food. Food irradiation is a method used to preserve food and make it safer by exposing it to ionizing radiation, such as gamma rays, electron beams, or X-rays. This process does not make the food radioactive. The radiation simply passes through or is absorbed without leaving any lasting radioactivity behind. So, what actually happens to the food? The radiation damages the DNA of bacteria, molds, and parasites. This stops them from reproducing, effectively eliminating harmful microorganisms. At lower doses, it can slow down ripening and prevent sprouting in foods such as potatoes and onions. At higher doses, it can sterilize food, which is similar to heat treatment. One major advantage of food irradiation is that it doesn't rely on high temperatures. This means that food can stay fresh longer while maintaining its taste, texture, and nutritional value better than some traditional methods like canning or pasteurization. Because of its effectiveness, organizations like the World Health Organization have confirmed that food irradiation is safe when used within proper limits. Today, many countries use it for products like fruits, vegetable, meat, and spices. However, the idea of radiation in food can make people feel uneasy. To address this, irradiated foods are clearly labeled, and ongoing research continues to improve safety and efficiency.